So welcome all. Today we are seeing something about distance vector routing protocol. So basically here you have to see that in internet, as you know, there are certain autonomous system we have divided, and within this autonomous system, when we route, we call it intra-domain routing, and there is something called intra-domain routing. So distance vector routing is basically intra-domain routing, you know? So now there are certain routers, and we have to apply some techniques so that these routers could get updated. Now you can understand one thing, that when we send some data, some packet from one router to another, then what happens, we keep some information of the path. We try to find at a particular router, we try to find the optimal path, right? So we will this distance vector routing protocol will help us in finding in updating these routing tables automatically, right? So now in this video we are discussing about Bellmen-Ford algorithm, and then how Bellmen-Ford algorithm is being used in distance vector routing algorithm. And then there is something called count to infinity problem. We will discuss it. So let us assume this is a graph where certain nodes are there. Let us assume these are routers, and this is the link between them. And these are the cost of routing, right? In place of these things, I can say, let us assume it as cities and road. So if these are the different cities and they are roads, these are the costs. So reaching from one city to another, you will have to go through certain path, and you will sum up all the cost to find the cost related to reaching from one city to another. And if I will say to find minimum cost to reach from one city to another, you will try to find out those paths using which you can reach in less amount of less cost, right? So Bellman-Ford algorithm actually helps in finding out the path from one node to another, which is of low cost, optimal path. Yeah. So here what you can say is, actually it is based on one fact. Okay, see, if all the neighbors of node I know the shortest distance to node J, let me see here, this is I and this is J. So from I to J you want to find the route. Let us assume all these nodes, neighbors of I, 1, 2 to n, they have a shortest distance. They have the information of shortest distance or optimal path from them to J. Okay. So if we assume that these have the information of optimal path, then we have just to find the cost from I to this node, right? I to this node, I to the other node. And then if we try to see the cost I1 I should say, I1 plus Dij. Okay, so if we add Ci1 plus Dij, it will give us some value. Ci2 plus D2j, distance from 2 to j. If we add these two values, it will give us some value. Similarly, we will add all the distance through all the intermediate nodes, all the neighbors of I. So n neighbors, so n distances we have, right? So this value plus this value for this plus this value, and then if we find the minimum value, whether this is minimum or this is minimum or this is minimum. So we are writing here distance from I to j will be the minimum of C I1 plus 1j, I2 plus 2j, or In plus nj. Whatever among these, whichever will give us the minimum value, so we will take that particular distance or path. Now the question arises, okay, whether really these nodes 1, 2, 3 and whatever they are, they have the optimal path. If not, one thing that we can do is we can iterate it. We will iterate it and try to find out the neighbors of 1 and the distance from them to j, and find the optimal path till here, and then we will update it. So this is what we can do in Bellmen for algorithm. Initially we will initialize it with all zeros, and sorry, if the cost is 0, right? If the I is equal to j, in that case we are saying the distance is 0. Otherwise the distance between these two nodes, if they are not same, then the distance is infinity. Then we come for updating. We repeat something. Till when? Until there was no change in previous iteration. In the previous iteration, whatever we have got the distance from I to j, if it doesn't change, then we stop. Till then, what we are going to do? For all the combination of ij, we keep the minimum distance. Okay? We can understand the neighbors, right? So I1 to 1j, In to nj. So whatever distance we are getting, we will update it, and so we will have the minimum value in the dj. Until it is changing, we will repeat. That is the thing. Now this Bellmen algorithm, similar kind of thing will be used in distance vector routing, right? Hello? So in distance vector routing, actually what we have to understand is say the cost. Cost between two nodes means cost between two routers is actually 1, right? Hop count will be considered as cost. So cost is actually 1. So table I dot cost is 1. Destination address is there. Next is okay. It's okay. We will see what is next. Then send a record R about each row to each neighbor. Okay, they will send the information to each other. Okay, so this will happen in start. We will see it in figure also. So in a start it will send we will understand the cost between 1 to 2 the neighbors will be 1, and they will share information with the neighbors. No issues. Now each router needs to update also, right? So for updating, what will happen? Whenever it will receive some information from its neighbor, it will update its own routing table. So you can understand that for each router, what it has to do, it will execute some part of the whole algorithm in Bellmen algorithm, right? has to update its own table, so it has to find the minimum among the from the neighbors. Right? That is the only thing. Whatever the cost of neighbors are there available at a current distance, it will adjust its own update table with according to the values of the neighbors. So after a router has updated, what it has to do, it will again, let me see. Send a record R about each row to each neighbor. It will send the information to the neighbors. No problem. Now these are certain things you have understood. Destination address, okay, the cost, and the next hop. These are the three information that every this router should keep. What are the three information? Destination, cost, and the next hop. So whenever the table will be there, in this table you will have three entries: destination, cost, and the next hop. So here what you will insert, destination will be the destination of the record. Whenever the record is coming, according to the record you will have the address. You will see if the cost is, okay, this is the updation. I will show this thing in next slide actually. What are the updation rules when it is being updated? Let me show you actually. So when it is updated, see if the next node entry is different and if the node entry is same. So if the next node entry is different, then we have to understand that the receiving node chooses a row with a smaller cost. Means the next node of, see, there are two nodes A and B, and they want to reach some node E. Now the next node is different, means A reaches E through D and B reaches E through C. So here it has to decide that if the cost through B, and if A can reach B and from B through C it can reach E, if it is less costly, then we can leave the D and we will consider the B, right? So that is the thing we have to understand, that the receiving node will choose the row with the smaller cost. If there is a tie, the old one is kept. Okay, from both the paths, this thing cost is same, then it is okay. If the next node entry is same, okay, A is also going through D and B is also going through D. In that case, what will happen? The center of the new row is the provider of the old entry. Okay, so the receiving node chooses the new row even though the new value is infinity. Okay. So when this information is shared, there are two ways: periodic update, periodically after 30 seconds or something, whatever fixed. Normally it is 30 seconds, so whenever after 30 seconds it will automatically send their routing information to each other. Triggered update can be there, that something happened, a routing table was updated recently, then it will trigger, it will send the information to the neighbors, or some failure occurred in the neighboring link or somewhere, then it will send them this information. That is the thing you have to understand about distance vector routing. Now see, let us consider this example where these are certain routers. This is one autonomous system, and this is, we are discussing distance vector routing. Sorry, distance vector algorithm, where this is the initial condition. Uh, what I'm saying is this each router creates its own routing table whenever it is booted. So it is not necessary that it is synchronous, all of them has to create at the same time. No, they will create whenever they boot. So now these routers have to update their tables. Initially this is something what it has. A has some entries 1, 2, 4 and 5. B has some entries 2, 3 and 6. It says that 2, 3 and 6 I can reach network 2, network 3 and network 6 in one, okay, directly. So network 2, network 3 and network 6 here somewhere, okay. Then what is happening is we have to update these tables. What will happen? Assume router A sends 4 records to its neighbors. You can see here router A has 4 records, and these neighbors are B, these and these, whatever. So it will send this information to B. Let us see what happens if it sends the 4 information to B. It will send these 4 records to B, D and C. So now you will see this image here. A and B are there. A has this thing and B has these 3 records. So what is going on in B's routing table, you will see. See, first it will send. So network 1 was there. Here we were not having network 1. So what happened? Now you will have to make an entry that to network 1. Now the cost is 2. Why? First one hop to A, and from A you can go to network 1 in one hop. So 1 plus 1, 2, cost is 2, and the next hop for going to network 1 is through A. Okay, you have made this entry. Now next packet is going for network 2. Okay. So when it came here, network 2 in one hop, network 2 was already here in one hop. So what happened then? You are not making any changes. Now the third record, which has network 4, one hop. Here there is no network 4, so we understand what can happen. This record will come here, and network 4 will be kept here. Network 4 with 2 hops. The next record is this network 5, one hop. It will come here. We understand network 5 is not present here, so what will happen? Network 5 will be made an entry here, network 5 with 2 hops. So that is very simple algorithm, distance vector routing algorithm. And this is something which what is happening. A sends some its record to B, C and D, and then also these all will share their information with each other, and it will be repeated, right? So in last what will be the final routing table? See, for A it will have all the information of all the networks. It has to go for network 2, it has to go from B. For network 6 and 7 it has to go from C. Similarly, network for routing table for B, C, D and others. So this was your distance vector routing algorithm. Now we are going towards count to infinity problem. Actually, you can see this is a network where two routers are there, A, B, and another router X. Okay, we are taking this. We are assuming that X is going to fail. Okay, in the next step it will fail. So now let me see the table. Table at A, it says it can reach X in one hop. Okay, directly. B has an information I can reach X in two hops with through A. No issues, no problem. Now the failure occurred. There is no link between A and X. So what happened? The cost from this place A to X is infinity. Okay, and the cost from X was, sorry, cost from B to X was 2 through A, right? Now this information was passed to B. So B updated its table and said that we can go, since B is there, B has an information that it can go in two hops. So let us update it, and we are writing we can reach X in three hops. In one hop I can reach B, and from B there is a path in two hops. So from X, sorry, 2X we can reach in three hops. Okay, now this table has been updated, so this information should be passed to this router also. So what will happen? This router will be updated. This routing table will be updated. It says that this router A has updated its information that it can reach, since A can reach in three hops. So 3 plus 1, I should say, we will reach in 4 hops. Similarly, this will continue, and what will happen? Ultimately, it will become infinity. Okay, so this is count to infinity problem. So somehow you are reaching to infinity. Then in this case, what you can do is something. Let us assume first of all that what the infinity can be is can we define infinity? So in most of the implementations, we actually define 16 as infinity. Okay. Now understand what we can call as a split horizon. Instead of flooding the table, what we can do, we can send only a part of the table through each interface. Okay, so what will happen? Assume node B thinks that the optimum route to reach X is via A, right? So it does not need to advertise this piece of information to A, you know, that is the thing. So now in a split horizon we will have certain problem. Say normally in this distance vector protocol, what will happen? We have a timer. So if there is no news in between that particular time, then what will happen? The node deletes the route from its table. Okay, so as in a split horizon, we decided that we will not send that piece of information to it. So if it is not no news for that particular about that route, in that case they will delete that route. So in the previous example, as we have seen, node A cannot guess that this is due to a split horizon, or because B has not received any news about X recently. Okay, it has no information. Now what is Poisson reverse? Node B can still advertise the value for X, but if the source of information is A, it can repeat the distance with infinity as a warning. Okay, now let me tell you about what can happen if you have 3 nodes A, B and C, and this X is going to fail. So let us assume this X is going to fail. You can see the tables that from A you can reach X in one hop, from others you can reach X in 2 hops through A. So now what happened, X failed, so A will send the information to others that this is something. And we have seen earlier in poison rivers that we will keep infinity as warning, right? So let us assume we have that information, we are keeping infinity there in B, but somehow this packet to C is lost. Then what happened? The C has information that we can reach X in 2 hops through A. Then what will happen? C sends the route to B. Now B has this information that we can reach in 3 hops through C. Now what can happen? From A we can reach in 4 hops. Now this A has updated, so C will also update, and this loop will count to infinity. So if the instability is between 3 nodes, stability cannot be guaranteed. I mean, earlier we saw that we will try something, we will split horizon and all this kind of thing. But if it is happening between 3 nodes, then there is a problem. So this is count to infinity problem related to distance vector routing algorithm. This is all for now. We will see the other protocols in next video. Thank you.